So today in module 2 we are going to study about the bending of beam or bending of beams. So what is a beam? When we consider a body whose length is larger compared to other dimensions, means if we consider the breadth and the thickness, the length is long, it is, and the body is having a uniform cross section, then it is called a beam. So if I read it, a homogeneous body of uniform cross section whose length is large compared to the other dimension such as breadth and thickness, then we call it as beam, and the figure what we have shown in figure 1. So the beam is, one end is fixed to the rigid support and the length is large compared to the breadth and thickness. Now these beams we consider to be made up of number of thin films or the planes parallel to each other. If you consider one body, cut it into very thin film planes. So what we consider that beam is made up of a large number of planes which is parallel to each other. It is like one slab you place above the other parallelly to each other. So if you consider as a whole, when the length is large compared to breadth and thickness, it is a beam. So what we say that the beam is considered to be made up of large number of thin films or the planes which are parallel to each other. Now if we consider the one such plane, we can assume that that plane is made up of long straight thin filaments. Means one such plane also if you consider, you can consider, if you consider a thread and you place the thread very close to each other of the same length, so what you can make? A plane. And then that planes, the similar structure you place over each other, what you can make it? A beam. So the layers of a planes are considered to consist of a large number of very thin filaments which is long. Now in the drawing you can see we have one such beam and you have three planes. If you divide it in different planes, one such plane it is shown here. So this plane is consist of the filament AB, CD and EF. There are many such filaments you can consider it. What we consider that CD is a neutral axis. CD is a neutral filament, and above this filament CD we consider the filaments from the upper layer, and below CD we consider that the filament forms the lower layer. Now when you apply the load, what it happens? When you apply load on something, it will bend, the beam will bend, or load, in another words if you say that if you apply the stress, there will be strain in the filament. So what we understand here, if you consider this figure, then we assume that if something you bend, something is a straight, you bend like this, so what it will happen? The upper layer will get elongated and the lower layers will get compressed. But we have to take a reference layer from which we can consider that how much elongation has happened in the upper layer and how much compression has happened in the lower layer. So one such layer CD, what we consider is a neutral layer or a neutral filament where there's such any change doesn't happen. So if we take this reference layer CD, we call it as neutral layer means the layer with which CD is made is a neutral layer, and CD we call it as neutral axis. And A dash B dash, what is after the elongation, what is the change in the length in the AB filament is A dash B dash, and what is the by how much the EF is got compressed is E dash F dash. So change you can find it out, A dash B dash minus AB will give you the change in the AB layer got elongated due to the application of the load or due to the load what strain is produced, and E dash F dash layer you can subtract it from EF and you can find out how much it got compressed. So we have considered a plane AB, CD and EF. Now when you apply the load, what it happen in the third figure, what you see, you apply the load, what you see that AB gets elongated and the new length is now A dash B dash, and the layer EF gets compressed to E dash F dash. So you can find the change in the upper layer there is elongation, in the lower layer there is compression. So the filament AB gets elongated to A dash B dash and the filament EF gets compressed to E dash F dash. So to find out the change you will have A dash B dash minus AB, you will get the elongation and if you subtract E dash F dash from EF, you will get the compression value, means how much the upper layer got elongated and the lower layer got compressed. Now here CD, which we take it as reference layer, what we assume it is neutral, there is no change in the length while the load is applied. So this CD we call it as neutral, this CD the plane of which is made we call it as neutral plane, and this CD we can call it as enclosed in one plane, so we can call it as neutral filament, or the CD with the axis which passes through the plane of which CD is made. So that particular filament itself, the line which is passes through the filament, we can call it as neutral axis. So you have to remember three things: the plane in which the filament CD is enclosed we call it as neutral plane, we can call it as neutral surface as well. Neutral means it won't change in the dimension when the load is applied. The CD itself we call it as neutral filament, and the line which is passing through the CD we call it as neutral axis. So how we can define the neutral surface or neutral plane or the neutral axis? We'll write that. So neutral surface we define as that layer of the uniform beam which does not undergo any change in its dimension when the beam is subjected to the bending within the elastic limit. Means that surface, as I explained earlier as well, it won't change either in length, breadth or thickness. That surface we call it as neutral surface, and one such filament of that surface is your CD. Now what is neutral axis? Is is the longitudinal line along which the neutral surface is intercepted by any longitudinal plane in the plane of bending. So, the axis passing through the plane which is neutral, that is what we call it as neutral axis, and that axis is nothing but a longitudinal line, and the plane on which it lies also is longitudinal. So, now we will learn what is force of reaction and the bending moment. So, what we know that every body, by the virtue of its phenomenon of elasticity, whenever the force, means the applied force on the body is removed, it has tendency to retain its original dimension. So, it is because of the restoring force what it acts when you deform the body. So, as soon as you remove the applied load or the force which deforms the body, the material retains its original dimension due to the restoring force what it is acting due to the applied force. Now, what we have learned that if we take a beam and apply the load to it, it undergoes bending, and we have taken one such reference layer to which the CD is a filament, and we also say that the neutral to this filament CD is a neutral axis, or the neutral axis passes through the filament CD which belongs to the neutral surface or the neutral plane. Above the neutral plane or the neutral axis, the above layer we understand it undergoes elongation, and the lower layer it undergoes compression. So, due to the elongation, an inward force of reaction acts in the inward direction, means along the fixed end, and which in turn will try to retain its original dimension when the load is removed. Now, in the lower layer what we understand means the layer below CD it undergoes compression. So, if it undergoes the compression, a force of reaction, that is an outward push, acts in the direction opposite to the fixed end, so that as you remove the load, the force of reaction will help in retaining the original dimension of a body, or in this case the beam. So, here what we understand that due to elongation and compression, the force of reaction comes into play due to the elastic nature of the body. So, the force of reaction means in the upper layer, the direction of the force means it will be in inward direction. We can call it as inward pull, which acts towards the fixed end, and in the lower layer where there is a compression, an outward push, that is the force of reaction in outward direction acts away from the fixed support. One is in force of reaction is in the inward direction, means towards the fixed end, and the force of reaction in the lower surface it is in the direction away from the fixed end. So, this inward and outward pull, what we call it as force of reaction, it leads to the restoring couple in the beam. What we mean by couple, it is nothing but a torque which is acting on the body. And what is the torque? It is the force which is applied to the distance perpendicular from the fixed point of a body. So if this is a body and this is what inward direction the force is applied, so force multiplied by the distance between the fixed support and the point where the force is applied, that will give the magnitude of the torque or the couple. So the restoring couple acts in the body to balance the applied couple acting on the beam, which is nothing. Applied couple arise due to the applied load. Restoring couple which balances the applied couple acting on the beam, the balance between the applied couple and the restoring couple is known as the moment of the restoring couple, which arise due to the restoring moment. The moment of applied couple which is subjected when the beam undergoes bending longitudinally, we call it as bending moment, and at the equilibrium the bending moment will be equal to the restoring moment. So in short, what we can say, that when we apply the load to the beam, in the above layer the force of reaction is in inward direction to the fixed end, and the force of reaction in the lower layer it is in the outward direction, that leads to the restoring couple, and this restoring couple arise to balance the applied couple acting on the beam, and in turn leads to the moment of the restoring couple or the restoring, that is what we call it as restoring moment. The moment of restoring couple is what we call it as restoring moment. So the moment applied to the couple is subjected when the beam undergoes bending longitudinally, we call it as bending moment, and at equilibrium the bending moment will be equal to the restoring moment. So this bending moment or the restoring moment, it is due to the force of reaction which acts in inward or outward direction when the beam is subjected to the load, and this force of reaction is due to the elastic nature of the body. So now we will derive the expression for bending moment of a beam. As usual, I have explained this figure is when no load condition, means when the load is not applied, and the another figure is in the case when the load is applied and beam undergoes bending. In the case of no load, if you consider the filament A, B, C, D and E, F, the length of these filaments will be equal. AB will be equal to CD and that will be equal to EF. Next we will, if we consider that the load is applied, when the load is applied and beam undergoes bending, both the case we are explaining for the beam. Due to the bending, the upper layer filament AB undergoes elongation and the new length is now A dash B dash, and if you have to find the change in the length, that is nothing but the strain, change in length, which you call it as longitudinal strain, that will be equal to A dash B dash minus AB. And similarly what we can say, that EF under has gone compression and the new length is now E dash F dash, and the change in the length will be EF minus E dash F dash. So we will take the reference of the upper layer for the derivation. Now we will consider that these layers which are bent due to the application of the load is part of a concentric circle which is subtended to the angle theta with the origin. We say, taking the reference layer as the neutral axis, means the layer CD or the filament CD, we say that the radius from this filament CD or the axis, neutral axis, is R. And similarly, as the length of OC is equal to R, the length of OD will be also equal to R. So we consider that the layers A dash, B dash, CD and E dash, F dash is a part of a concentric circle which makes an angle theta with the origin. O. So we can say that length OC is equal to OD is equal to R, the radius of the circle which is made by the CD. And also we will consider the distance between the layer to which AB filament belongs to is R. Means if we consider C A dash, that is equal to D B dash, and that is equal to R. So if we want to find the arc length CD and A dash B dash, what we get? CD is equal to R into theta, and A dash B dash will be equal to R plus R into theta. Now what we know, this length CD can be written as it is equal to original length of the upper layer AB and it is equal to EF. We have written AB is equal to CD is equal to EF. So what we can say, that the change in the length due to the bending, that will be equal to A dash B dash minus AB. So if we try to find out change in length, this is equal to A dash B dash minus AB. This will be equal to R plus R into theta minus R theta. So we get R theta plus R theta minus R theta. So this gets cancels out and the change in length is equal to R into theta, small r into theta. And if we want to calculate the longitudinal strain, it will be equal to change in the length divided by the original length. So what is the change in the length? It is R into theta, and the original length means length of CD or AB or is equal EF, that is capital R into theta. So divide by R into theta. So we get longitudinal strain as theta theta cancel out, R by R. So then Young's modulus which we define it as longitudinal stress divided by longitudinal strain. This will be equal to longitudinal stress, what we define it as force per unit area, and longitudinal strain, change in the length divided by original length. So, if we assume that the bending means stress is nothing but force per unit area, A is the cross section where the force is applied, and if we take longitudinal strain, so we can write it as R divided by R. So, what it will be? Here we can write it as R by R, and we define Young's modulus by capital letter Y. What we need is the expression for force. So, further solve this equation. Force will be equal to Y by R into AR. Force will be equal to Y into A into R divided by R. So, force is equal to Y by R, A into R, where A is the cross section where the force is applied. So, next we have to find out the moment of force, which is nothing but the bending moment from the neutral axis, which will be equal to the applied force multiplied by the perpendicular distance. Moment of force will be equal to F into R. R is the distance between the neutral axis and the upper layer filament A dash B dash, which has undergone a change, or E dash F dash, which has undergone a change due to the applied load. So, we know the expression of force, what it is, Y by R, A into R, and this multiplied again by R. So, moment of force Y by R into AR square. So, bending moment we can write it as Y by R into AR square. If we calculate the total bending moment of the beam, then it will be Y by R and summation of all such cross section where the force is applied. That moment of inertia is equal to sigma mr square. Moment of inertia, and we introduce or write it by Ig, the bending moment we can write it as Y by R into Ig, where Ig is equal to sigma AR square, and this we can write it as A K square, where A is the total cross section of the beam and K is the radius of gyration. So equation 10 is the expression for the bending moment of a beam. Now if the beam is of particular size, whether it is rectangular or whether it is circular beam, depending on that the Ig value, means the geometric moment of inertia, it changes. If the beam is rectangular, then Ig is equal to BD cube by 12. When the beam is rectangular in shape, then Ig will be equal to BD cube by 12, where B is breadth and D is the thickness of the beam. So what we get? In the case of rectangular beam, the bending moment will be equal to, from equation 10, y by r into BD cube divided by 12. And if the beam is circular, then Ig so then what we get? Bending moment is equal to y by r into pi r to the power 4 divided by 4. So this equation 10, 11 and 12 are the expression of bending moment. Equation 10 is the expression in general. Ig you can calculate for any shape of the beam. So when the shape is rectangular, Ig is BD cube by 12, and when it is circular this way, you can consider this is a beam, circular beam, and the flat beam we can call it as rectangular beam. So if the beam is circular, Ig is equal to pi r by to the 4 divided by 4, pi r to the power 4 divided by 4. So when you substitute the value of Ig, accordingly you will get the bending moment as per the shape of the beam. So coming to the types of beam, we are going to study here about 4 types of beam: simple beam, continuous beam, cantilever and the fixed beam. So what is simple beam? Simple beam which has supporting at the 2 ends, that is what we call it as simple beam. When the beam has more than 2 supports, we call it as continuous beam. When the beam one end is free, so that we can apply the load, and the other end is fixed, we call it as cantilever. And the beam with both the ends are fixed, that is we call it as fixed beam.